Alright, hi. My name is Abdurrahman Nasif, or you can call me Budi. I'm a third year Energy Systems Option Engineering Science student at the University of Toronto. And this is going to be my Quirky Connections video. So the video talks mainly about water and the different properties of water. And in particular I talk about the mixture of water between the states of gas and liquid. So essentially water has a huge amount of different properties, and that's what makes it really special. Water's density peaks at 4 degrees Celsius. So if you have water essentially at 25 degrees Celsius and you cool it, it will cool at a more or less linear rate until it peaks and reaches maximum density at 4 degrees Celsius. And if you cool the water beyond 4 degrees Celsius, the density would actually drop. Another interesting property of water is it has a really high specific heat capacity, meaning it has a huge potential to store energy. This results in creating winds and waves on the surface of the earth, which is really important because not only that, but water is also a great solvent of organic matter. And so you need these winds and these waves to transport this organic matter from one place on earth to another. And this essentially gives life. Now water, just as any other substance on earth, can exist as a gas, liquid, or solid, or as a mixture between any of these three states. So liquid can be trapped, can be dissolved in gas as water vapor. Gas can be dissolved in liquid, and you can have gas trapped within an ice cube, which is gas trapped within solid, and the same for liquid. And mixtures between these two, and between any two states, especially for water, can give us very interesting results. So over here I'm going to show the Bernoulli equation. And the Bernoulli equation essentially relates pressure of any liquid or fluid to the velocity of the fluid. So if you've ever visited Niagara Falls, you'll notice that as the water falls from the top of the waterfall to the bottom, a lot of gas is released. Essentially, if we use Bernoulli's equation to analyze this, we understand that the water at the top of the waterfall is at very high pressure. And the higher the pressure of the water, the more air it can store. Also, the colder the water, the more air it can store. And so as the water falls from the top of the waterfall to the bottom, its velocity increases. So its pressure, or its potential energy, is traded for its kinetic energy. And now it has a higher velocity, but a lower pressure. So consequently, the air trapped within the water is released to the atmosphere. And that's why we see all this air. Now the colder the air, the colder the water, the more air it can store. And so if it's very cold, and the same process occurs, you'll notice that there's more air being released. Whereas if it's warm, if the water is very warm, less air would be released. Now in this video, we'll conduct a few experiments using this water bottle to see the effective temperature and pressure on the amount of bubbles that form on the surface of the water bottle. So the experiment is conducted with three different scenarios: low velocity hot water, low velocity cold water, and high velocity water. And comparing these three different scenarios in terms of the amount of bubbles that form on the surface of the bottle, we can understand the different properties of water and how the state of the water, how we can use the state of the water, its temperature and pressure, to determine the gas content, how much gas or air is dissolved in the water. So right now I'm going to show a video of me performing the experiment. But before that, I'm going to show you a brief overview of how the tap works, how opening the actual knob of the tap at different levels to different extents can change the velocity of the water coming out of the tap, and how the different pressures and temperatures how we can obtain different temperatures and pressures from tap water. Alright, so here's the tap, and basically we have the hot water supply on the left and the cold water supply on the right. So any water that comes in from this pipe up to the tap, which we open from here, is hot water, and consequently it has less air content. Any water that comes from this tap over here is colder water and has more air dissolved in it. If we look at the actual tap opening, we can see a little mesh over here. Basically this mesh, so the water, before the water exits the actual tap, it's pressurized, and that's like, it has to be pressurized, so it reaches from the base of the building to the tap up here. And when we open the actual water, stagnation occurs over here, so it acts pretty much as a nozzle, and the velocity of the water increases. Now, the reason we feel that, like, the greater the velocity of the water, the higher the pressure, is that when we actually feel the water, stagnation occurs at our hands. So the kinetic energy is exchanged for potential energy, and instead of having high velocity, you have high pressure on your hands. But before the water reaches your hand, it's high velocity, not high pressure. So if we open the water slightly, you can see that there's no bubbles forming, it's just a uniform stream, like this. But if we open the water to a greater extent, because the velocity is much higher and then stagnation occurs at the mesh, the pressure is much lower, the pressure of the water is much lower, and the velocity is higher. And so bubbles start forming because the water is unable to contain the same amount of air, like so. So I'm going to start with the low velocity cold water situation. So this is scenario 1, low velocity cold water. I'm going to place it here to see how the amount of bubbles that form over time. And this should be related to the Bernoulli's law, because we know that the higher the pressure of the water, the more air is trapped within it, and because air is pressurized so that it is pumped, the water is pressurized so that it can be pumped from the base of the building to the top of the building. Releasing it should decrease its pressure. So now the pressure decreases, we should see bubbles forming in a while. So now we can already see the bubbles forming on the surface of the bottle. And if you notice, most of the bubbles rise to the top of the bottle, just due to the difference in density, while some bubbles stick to the surface of the bottle. Right, so this is after another 2 hours from the previous video, and as you can see, the bubbles have increased, but then it's probably going to peak at this point. Okay, now the reason that the bubbles are clinging onto the sides of the water bottle is because there are imperfections in the actual material, and so that creates pockets for the water bottle. But if a certain distortion is created, or a vibration is created in the water, then all the bubbles rise. Again, due to the change in the difference in density. So, like so. Yeah. So most of the bubbles are gone. This is low velocity hot water. Now I'm going to retry the experiment using hot water, and based on the differences we see between the hot water and the cold water, we're going to draw conclusions. So as we can see, the warmer water, which is now at room temperature, form much less bubbles on the surface of the water bottle than the colder water. And finally, scenario 3 is high velocity water. Notice that we only do one scenario for high velocity water because the air inside the water is released as soon as the water settles inside the bottle, regardless of whether the water is hot or cold. So as you can see, when we release the water from the tap at high pressure, most of the bubbles form as the water deposits into the bottle. So we don't find any bubbles forming at the surface. Alright, so just to end on an informative note, we saw that cold water has a lot of air content in it because there's a lot of oxygen dissolved in the water, and hot water doesn't. So when we essentially when we pour the water into the bottle and we leave it outside, the high pressure water becomes unpressurized, and so gradually the water is released from the air is released from the water. And for the cold water, gradually the water cools down, and so it has less capacity to contain that air, and so we get bubbles forming on the surface of the water. And so that's why if you have cold tap water, it tastes much better than hot tap water. But if you have cold water and you leave it out for a long time, it doesn't taste as fresh because all the bubbles are no longer dissolved in the water. And that's it for my Quirky Connections video. Thank you for watching.